Einstein wasn't a fantastically good mathematician.
That's Tim Palmer, and every time you open up your weather app, you're using one of his mathematical ideas. He pioneered ensemble prediction systems for weather and climate. In his book, he points out that the butterfly effect isn't just small things being able to have big impacts or effects, but also you have to determine which small things will actually result in something like a tornado. One of my favorite moments from our conversation is when he explains how he figured this out using a very simple picture. So, if you're trying to build a career doing original science or want to understand how leading physicists break down difficult problems, then I think you'll really enjoy this conversation. Do you think it's possible to, say, if we wanted to turn like a low order chaotic system like uh, planets and how they orbit into like a high order chaotic system like turbulence, do you think we could add like a bunch of, I guess, scaled up and down planets and like a billion of them? And would that have the same, I guess, like chaos as turbulence, or like are they fundamentally different?
Uh, uh, I mean, it's a difficult question to answer precisely, but I would say, in a way, that the underlying equations are a bit different. I mean, in the case of turbulence, we have these equations called the Navier-Stokes equations, which, in a way, are fairly simple. I mean, they're Newton's laws of motion with forces that occur in a fluid, so pressure forces and molecular viscosity and all this sort of stuff. Um, they're written down as what we call partial differential equations, which means that they kind of have an infinite number of degrees of freedom, and that's what makes turbulence a very difficult problem to simulate mathematically and even to understand. On the other hand, planets, I mean, it's an inherently finite system, but more than that, the force of gravity is this very specific, well, in Newtonian physics at least, is this very specific inverse square law, which I don't think you see specifically in the Navier-Stokes equation. So, yeah, no, I think they're kind of different problems, but they're both chaotic. I mean, there are lots of systems, can be chemical systems, biological systems, physical systems that are chaos, and there are lots of different types of equations which all have this property of chaos. Chaos is a fairly kind of generic property for nonlinear systems, I guess. I mean, that's the main kind of thing. They have to be nonlinear. Um, but no, I would say in a way, fluid turbulence and planetary motion are. I mean, although they're both chaotic systems, they differ from each other in the detailed equations that you have to solve.
And I guess, like, why is winning that $1 million prize from the Clay Mathematics Institute so hard? Like, what makes the Navier-Stokes equation so hard to solve? And have you tried to solve it? And how come it hasn't worked?
Well, uh, it's kind of it's. I mean, it's hard to pin down like precisely why it's so hard, but it's linked. Again, I come back to this point. It's linked to the fact that it's an infinite dimensional, non-linear problem where scales are interacting, um, and and I have to say, I mean, the difficulties are subtle ones because if the fluid was a two-dimensional fluid, so if in one dimension it was like, say with height, if the fluid was the fluid velocity was exactly the same at all heights, so the fluids was two-dimensional, then actually one can prove the like this $1 million prize. Well, if the $1 million prize applied to a two-dimensional Navier-Stokes, then it would have already been won. But of course, it only applies to the three-dimensional problem. So people haven't done that yet. Um, Yeah. Uh, uh, yeah, it's a very. I mean, one only has to look at the the attempts to solve it, and you very quickly see that the mathematics is extremely complex and uses very advanced ideas in a field called functional analysis. So you have to be, I would say, a very strong mathematician to even attempt to try to solve it. And I don't consider myself to have the required uh, functional analytic skills to even, well, I wouldn't seriously attempt to do it, but I know enough to know it's a complicated problem.
I heard you say that like Roger Penrose and also Dennis Sciama, they taught you uh not to, I guess, to think in like simple pictures and use geometric objects and not kind of be intimidated by the complicated mathematics. Um, is there like an example in your later work where you use this idea and it helps you kind of understand something that you were struggling with understanding?
Um, I mean, this was particularly Roger Penrose. I mean, he is a he thinks in terms of pictures and geometry, and then uh, if it gives him an insight, then he can work out he can go back and check that it's technically correct. Um, well, I would say a lot of my ideas in climate physics came from um, just looking at the geometry of the Lorentz, the famous three-component Lorentz model.
I'm going to show a few pictures here for context. This Lorentz attractor is a very simplified model of the weather, and as you can see, the system gets a lot more unpredictable depending on your position. And what Dr. Palmer is best known for is the development of these ensemble prediction systems, where you take a bunch of different weather forecasts and vary the initial conditions slightly. And this lets you see a bunch of possible weather outcomes. But you can't do this randomly because there are some zones that are way more predictable than others. You want to find the point at which the ensembles will diverge the most. If you imagine you pick randomly and you pick in all the same predictable zone, that doesn't help much. And I always wondered how he did this, and it turns out he uses this idea of singular vectors and he explains it.
Another, maybe this is a bit too technical, but I was discussing this the other day with people that I did a my undergraduate degree was kind of a joint mathematics and physics degree, and in mathematics you're taught in applied maths you're taught about certain differential equations which like the wave equation and the heat conduction equation, the diffusion equation. And all these equations are of a particular type, which are sometimes called Sturm-Liouville equations. And they have, if you like, if you write the operators associated with the differentials, they're sometimes called self-adjoint problems. The operators, the sort of like if you think of the operator as a matrix, it's kind of a symmetric matrix. And in physics, we were taught quantum mechanics, where basically a fundamental postulate actually of quantum mechanics is that all operators, all what are called observables, are these things called Hermitian operators, and a Hermitian is basically a self-adjoint operator. You just have to, it's like the same as the wave equation, but you have complex numbers, so you have to take the complex numbers into account. But it's basically, they're symmetric types of operators. So, one kind of comes away with this idea that everything in physics and maths is describable with these by these kind of Sturm-Liouville type systems, and that if anything isn't Sturm-Liouville, then it must be sort of pathological. But I discovered in doing, in chaos theory and in fluid mechanics, pretty much, yeah, all of these topics, they're not Sturm-Liouville at all. And now you say, well, what's the consequence of that? Well, one of the properties of a self-adjoint operator, Sturm-Liouville operator, is that its eigenfunctions are orthogonal. And if you don't have that condition, then the eigenfunctions aren't orthogonal. And you might think that's a very technical kind of issue, but it has a really important consequence. And it's one that I didn't really understand until I just thought about it in terms of very simple pictures. And the point is that the stability of a system is not so how far. How fast perturbations can grow if you perturb a system. If it's very stable, a perturbation will decay in time. And if it's unstable, perturbations grow. Now, normally with Sturm-Liouville systems, you would say that, okay, if it's a stable system, then all the eigenvalues of the eigenvectors should be less than 1, so that the perturbations don't grow. However, if you have two eigenvectors, which are, and this is where a kind of picture would be useful, but if you imagine two eigenvectors as two arrows, but they're not orthogonal to each other. So I'm imagining a picture here of two arrows which are not orthogonal to each other. And these arrows represent eigenfunctions. And both of them, maybe both of them decay, but one of them decays, say, much faster than the other one. So you have one eigenvector which is maybe decaying a little bit, and the second eigenvector, which is not orthogonal. Just imagine these two arrows, say, at an angle of 30 degrees to each other rather than 90 degrees. Now, at initial time, you could imagine a perturbation which is the difference between these two eigenvectors. So it just points between the tips of the arrows. But now, one is decaying very slowly and one is decaying very, very quickly. What you would see if you just drew that on a piece of paper is that you will see the resulting perturbation arrow, which is joining the tips of the eigenvectors, is actually increasing in magnitude when they're not orthogonal. And that's telling you that looking at eigenvalues of eigenvectors to determine the stability of a system is completely useless when you're dealing with non-self-adjoint problems. And the point is that this is almost always the case in fluid mechanics and nonlinear dynamics. Anyway, so that's just an example of how a simple kind of picture can really transform one's thinking. In meteorology, I spend a lot of time calculating what are called singular vectors and singular values of flows to try these completely get over this problem of non-self-adjointness. And it just completely transforms the way you think about instabilities, and turned out to be really important in weather and climate dynamics.
So I'm just going to show the visual that he's talking about. So the way I like to think of turbulence is, say you have water moving really fast on top and then not as fast at the bottom. Then you can see it'll sort of want to roll over and create this type of turbulence. And we use matrices to kind of mimic what's going on in a fluid. So say if we were to put like a square through this matrix, then because the top of the square is moving faster, then it'll have this sheared type of shape. And now we finally get to the diagram of what he says. So when you're in this sheared, slanted environment, a disturbance, that red line, can grow even when both vectors are decaying, but one of them is shrinking faster. And this is important because in weather prediction, you probably want to place initial conditions in these unstable regions so you have the most diverse group of ensemble members possible. You said before that you don't think like you're like, I don't know, like a good enough mathematician. Like, sorry, I don't want to say this in like a weird way, but like to solve the Navier-Stokes equation. So like I guess if your talent isn't in like, this type of mathematics, like how come you think you were able to solve all these problems, and what kind of gave you an edge?
Well, look, I don't want to compare myself. It would be, this that would sound very conceited if I was to compare myself with Einstein. But Einstein wasn't a fantastically good mathematician. I mean, that wasn't his forte. I mean, he knew mathematics and he could use it, but he wasn't. Nobody would have said he was a mathematician. What he had was this phenomenally phenomenal kind of insight, well, phenomenal intuition, I think is the word I guess I would use, about, um, yeah, the way physics worked. And he also, I think, a bit like Penrose, would think in terms of pictures. Uh, and when he had an insight, which maybe came from thinking in terms of pictures, he would then consult mathematicians that he knew to formulate his insights in a more kind of rigorous way. And well, I'm a kind of lesser version of that. I mean, in the sense that I I don't tend to. I mean, I suppose there are certain types of people that maybe get really, really into some mathematical um, subject, and then kind of ask, well, how can I push this forward? Um, I guess that's not my way of thinking. I try to think about certain problems and try to think intuitively, how an approach that could solve that problem. And then I try to look for the maths that would do that. I mean, for example, I had this, like just now we were talking about how the eigenvectors of non-self-adjoint systems were not really helpful in determining the stability of a system. So that got me thinking about, well, what is the mathematics that is needed to talk about stability of non-self-adjoint systems? And that led to this whole area of what are called singular vectors and singular values, which is an area of maths that I'd actually never heard about as an undergraduate, but it was just kind of what I needed to um, yeah, to solve that particular problem. Um, so yeah, um, well, I don't know. I just feel in my own career, I do try to read widely. So I do know. I mean, I know quite a lot of maths, and I read a lot of maths stuff. So I'm aware of a lot of things, but I don't, in I don't kind of drill down into one mathematical topic unless I feel that I need it to express some physical idea. I don't kind of drill down into it just for the hell of it, if you like, or the sake of it.
Um, I guess another question I had is, how is being like a physicist temperamentally different than, I don't know, like playing a guitar in a band for you?
uh, well, I think the most important thing I would say is that uh, what they share in common uh, are things I enjoy doing. I mean, they're things I can easily spend several hours and not really notice the passing of time. And I think at the end of the day, it's super important um, to if you're doing research in a field, um, to do it because you enjoy doing it. Um, you because any I mean it's pretty much true of anything that you do in life. If you want to be kind of good at it, I mean, I'm not a professional level guitarist, but I mean, I can play guitar pretty well, I would say. Um, but you know, you only get there by spending a lot of time practicing, and it's similar. You know, as a research scientist, you only get there by spending a lot of time, and you've got to enjoy it. I mean, if you don't enjoy it, then everything's a pain, and if it's a pain, you're not really going to, you know, you're not going to progress very much. Um, so actually, in that sense, I would say the guitar, yeah, the guitar and the science um, are kind of similar in that sense that they're things I can sort of sit down and work out for a few hours and hardly notice that a few hours have gone by. Um, but of course, I mean, they exercise different parts of the brain, I suppose. Um, I mean, it's an interesting question about creativity in the arts and the sciences, whether they're similar or different, and we can have a discussion about that. But I would say the most important thing is that they're similar in the sense that I enjoy doing both of them, and I guess you know that's what I would say as a general remark. You know, trying to if you're moving into thinking about going into research, I mean, first and foremost, do it because you think this is a fascinating topic that you'll enjoy working on, um, rather than necessarily, oh, it's going to give me a job at the end of it or something. Do it because you enjoy it.
Um, I guess like with there was that chapter on like noise in the brain and how it could be used to uh, come up with creative ideas in the sciences. And do you think that like in music that that happens as well?
Oh, I'm pretty sure it does. I think that is the one thing you know that is probably common to all like arts and sciences that you know really creative ideas um, sort of almost you know come out of nowhere. I mean, you know, there's endless stories about Nobel Prize winners who, you know, had their eureka moment doing something totally non-scientific, and I think that's true. I think that's true if you go in the arts as well. You know, people, if you talk about where their kind of where the key idea came from, I mean, they're just, oh, I was walking along the road one day and it just popped into my head. Um, and this to me raises a really interesting question about, you know, AI and creativity. Um, and I mean, I, you know, I hope, I mean, I mean, it's true that AI, I mean, people use noise. I mean, people have stochastic algorithms in AI, but it's not really, noise isn't really at the bedrock of AI. You know, it's added here and there to perhaps help some of the algorithms not get too stuck in a particular rut. But my own view is that to really make AI creative, we've got to get the noise, the stochasticity down at a much deeper level in the system, and that really means going into the hardware. And there must surely be a kind of message here that you know the human brain works on 20 or something, 20, 30 watts of power, whereas a data center, you know, needs 20 or 30 megawatts. So there's a massive disconnect between the human brain and the AI kind of data center. And I think I don't think we'll really see true what they call AGI until we've got the potential, at least, for being able to run um, you know all the transistors at low enough energies that they start to become inherently stochastic. Um, so I think yeah, I think that trying to you know think about our own brains and how we get ideas um, is going to be important in designing kind of next generation AI systems.
Why don't you think like this idea of like a CERN for climate change, like that international organization, why don't you think it's, you know, already been done, or like what are the challenges of implementing it?
Well, I think it's needed, first thing I would say, because climate change is I mean, we're talking about the Navier-Stokes equations. I mean, that climate, the fluid, the fluid mechanics of the atmosphere and the oceans are basically, down to solving the Navier-Stokes equations. And in the atmosphere, it's especially complex because you have this problem that the air contains water, and water manifests itself in three different phases in the atmosphere as gas, liquid, and solid. Um, and all those things, whether the water's gas, liquid, or solid, affects massively how solar radiation, is absorbed or reflects or refracts or whatever. And also the latent heating of the atmosphere as it passes from one phase to the other, affects the circulation patterns. So we're dealing with a fantastically complicated system. And I always tell people that we have a pretty good understanding that as we emit CO2, the planet will warm. But exactly how that manifests itself regionally in terms of circulations and things is actually a much more complicated question. I still don't think we have much confidence in our understanding of the regional impacts of climate change. I mean, a good example of this is the thing called the Atlantic Meridional Overturning Circulation, which is one of the ocean circulations in the Atlantic Ocean, which is kind of responsible for Northern Europe having warmer temperatures, say, than the equivalent latitude in Alaska. But this circulation could be literally shut off by if the Atlantic water becomes significantly less salty than it currently is. This circulation could be shut off, and things like the melting of Greenland could do that, or enhance rainfall from storms that pass over the Atlantic. And this is an example of a tipping point that people often talk about. But the climate models just don't. I mean, the resolution is not really good enough to have reliable estimates of whether these tipping points will occur or not. So we're profoundly uncertain about that. And if the Atlantic thermohaline circulation switched off, it could actually have quite a big effect on the weather of Northern Europe, including the UK and the Northern European countries, and kind of completely reverse the warming effect. So my view is that this is a problem kind of up there with the Large Hadron Collider or some of the space telescopes and things like that, which is that it's a problem that would benefit from the countries of the world pooling resources and building the types of models and I mean, these days, by the way, computers are becoming, with the explosion of AI, computers are becoming expensive. And back in the old days when I started off in this field, there was a thing called Moore's law, which basically meant that the chips would get twice as fast every couple of years or so, but the cost would remain pretty much the same. So for the same amount of money, you could be sure that in a couple of years' time you'd be buying a computer that's twice as big. So you can plan for that. But now it's kind of going the other way. Moore's law, I mean, it's becoming more and more difficult to build, smaller transistors. They're right down at the atomic level now, so there's not much scope for making them smaller. But on top of that, the big explosion in AI means that the chips themselves are just becoming more expensive. So we've got a kind of a double whammy of the chips are not getting smaller, but they're all getting more expensive anyway. So I think maybe, all I'm saying is it's making the case for an international institute where the countries pool their resources more and more important. But unfortunately, there's politics gets a little bit in the way here. I mean, scientifically it makes perfect sense, but at the moment, of course, most countries, Canada included, have their own climate centre. There's a UK Met Office is the main climate prediction centre in the UK. Germany has the Max Planck Institute. Every country has its own climate center. So, the directors of these institutes are, they're nervous, I suppose, about endorsing an international center because they're worried that the money might come from their own budget. Let's put it basically. And so, yeah, it's been a very difficult sell. I mean, if no country had a climate modeling center when this notion of a CERN for climate change was first proposed, then I think it would have been a no-brainer. Everyone would have said, "Well, this makes sense. We'll just pool resources and we'll be able to do much better." Because that's basically what happened when CERN. You see, when CERN was set up. I mean, the UK had a particle accelerator, but most countries, didn't, and so there was a lot of enthusiasm to pool resources to build a international particles accelerator. But in the case of climate, there are these existing national climate institutes, and that's the political obstacle to making this happen.
Thank you so much for your time today.
Okay.